Okay, so what you're going to see on this page is just a quick summary of the graphs and sequences from the previous couple of slides. So we're going to use this information to start to kind of make some conjectures and see how these would work if we were talking about, possibly these modeling money in a savings account. So I'm just going to highlight these in 3 different colors. So we have sequence A, which was our linear function. I'm going to highlight in red. Sequence B, which was neither linear or exponential, we're going to highlight in blue. And then sequence C, which was our exponential function, I will highlight in green. So let's go ahead and look at this first question. It says, will an exponentially growing bank account, that's our sequence C, eventually contain more money than a linearly growing bank account, that's our red account, for the same amount of initial savings, no matter how fast or steep the rate of growth of the linear account? So then we would use our slope triangles on the left to try to help explain. So if you look at, let's say sequence A was growing at a really fast rate. So instead of growing at 27 every time, maybe it's growing at like 1 million each time. All right. But with sequence C, we have this growth rate that doubles each time, right? So eventually, even though that linear equation is growing by 1 million each time, because our exponential equation is doubling is going to have a bigger effect than growing by 1 million each time. And you could model this by looking at an equation of a line that has a slope of 1 million and a exponential equation that has a growth rate of doubling. And I can show you a picture of that in just a second. So on Desmos, I just did 2 equations. I did one of them that is y equals 1 million x plus 5. Okay, so my zero term was 5. My rate of growth for that linear function was 1 million. And then I did, for an exponential function, just kept it so that my rate of growth, my doubling, was just a doubling rate. So I did 5, which was my initial value, times 2 to the x. I'm doubling. And it takes a while, but eventually we see that the blue, which is our exponential function, will eventually overtake that red, which is our linear function. So it takes a little more than 20 years, but it does happen. Okay, so no matter what your rate is for a linear function, if you compare that to an exponential function, eventually that exponential function is going to overtake it. So when you have a choice, especially when you're talking about long-term investments, it is much better to think in terms of a exponential type of equation versus a linear type of growth. Okay, so that would be how we could answer that first question. And then how does the growth of a quadratic sequence like sequence B compare to exponential growth? So sequence B is a quadratic, and we haven't really talked about that yet. But the equation of a quadratic is just y equals x squared, is the most basic quadratic. So we can look at in the long term how those two would compare. So let's take a look at the 2 sequences and see how they would compare over the long term. So let's look at these 2 equations if we go out a little bit further. So we went out to 7 years, and at 7 years we saw that the quadratic, the green graph, was still more than the exponential graph. So at 7 years, we're right about here and here. And we can see that the green, the quadratic, still has a higher value than the exponential curve. But if we go out just a little bit further, if we go out to just over 7 years, we start to see that's where those 2 graphs would intersect. And then after that, your exponential function is going to have a higher value than your quadratic. Okay, so over time, once again, exponential is going to be a better investment. So how does the growth of a quadratic sequence like sequence B compare to exponential growth? It looks like it's growing faster, for the first few years. But then after that, the exponential function is going to quickly overtake and become a lot more than the quadratic would.